Welcome to this video on the Add More tool. Add More stands for Automated Dynamic Display of Measures of Risk and Error, and it's a tool that helps us evaluate time-dependent statistics. So it's an output analysis tool implemented as an Excel add-in, and it's available online for free on my website, negahban.com, which you can download and use for free. Also, if you would like to know more about the tool, you can refer to a conference paper published in the Proceedings of the 2016 Winter Simulation Conference for additional information about the tool. So in this video, we're going to talk about first what we mean by measures of risk and error, and then we'll talk about what tools are available to us through existing commercial simulation software packages to analyze how time-dependent statistics change over simulated time. And then we'll do a quick demo / tutorial of the Add More tool. So we're going to continue our discussion on the Add More tool in the context of a simple simulation model where I have two stations, each with a capacity of 1, that are connected in series. So all of the entities will first visit the first server. Once they're processed on the first server, 50% will randomly leave the system, and 50% will be randomly routed to the second server. And once they are processed on the second server, then they will leave the system. We've developed this model in the Simio simulation software package, which I'm going to show you shortly. But before I do that, let me also talk about the arrival process into my simulation model. So I have a non-stationary arrival process into my model. On this plot, what I'm showing is how the arrival rate, the hourly arrival rate, changes over the 12 operating hours. This system can be a simplified model of a restaurant where we have a lunch rush and dinner rush, for example. Also suppose that the performance measure that we're interested in is number in system at a particular time t. So we want to know how many customers we have in the system at a particular time t. So let's go to our Simio model. Here is my Simio model. I have a source object that creates my entities. I have my two servers, and I have my sink, and then I have probabilistic routing after the entities are processed on the first server, which I'm doing using link rates. Also know that I start my run at 10 in the morning, so I'm assuming that this restaurant opens at 10 a.m., and I run for 12 hours. So I stop the run basically at 10 p.m. And the other thing that I have in my model is a dynamic plot. And what I'm showing in this dynamic plot is my customer.population.number in system. So I'm essentially showing the instantaneous number in system, number of customers in the system in this plot as I run the model in the interactive mode. So let's go ahead and run this model. Again, what we expect to see is that we start at 0 number in system, and then during lunch rush, we expect the number in system to go up, and then the number in system goes down, and then again, once we get closer to the dinner rush, we expect the number in system to go down, and then it decreases. The other thing that I would like to mention is that in this model, I'm not going to deal with terminating conditions. In other words, when I stop the simulation run after exactly 12 hours of simulated time, I may still have some customers in the system that are waiting to be processed. While we do not deal with terminating conditions here, this does not have any effect on the things that we're going to discuss in this video. So again, suppose that my performance measure is number in system at a particular time t. So let's say at exactly 2 p.m., I would like to know how many customers will be in the system. And in this particular run, it turns out that I have around 60 customers in the system at around 2 p.m. But of course, this is only based on one replication of the model. So what I essentially need to do is run multiple replications of this model to be able to get statistically valid information about the number of customers in my system at this particular point in time. So that's what I've done. And what I have here is what we call a Moore plot of the number in system at this particular point in the simulated time. So the Moore plot, again, as you can imagine, Moore stands for measures of risk and error, is a plot that provides some information about, of course, measures of risk and error. So let's talk about the different components of the Moore plot first. So here we can see that the Moore plot is essentially a combination of a histogram and a box plot, but it also has some additional components in it. So here I see the histogram of my data. This is based on 100 replications of this model, where in each replication I record the number in system at exactly time t. And you can see the minimum, the maximum, the mean, the sample mean, and this beige box around my mean represents the confidence interval around my sample mean. You can also see the median, upper percentile, and lower percentile for the number in system over these 100 replications. And the blue boxes that you see around the percentiles are essentially the confidence intervals for the upper and lower percentiles. In this particular Moore plot, I'm using the 25th and 75th percentiles to generate this plot. Now, we refer to the confidence intervals as measures of error and the percentiles as measures of risk. So now what we're going to do is talk about what we mean by measures of error and risk and why percentiles are measures of risk and confidence intervals are considered as measures of error. So let's talk about confidence intervals first. So let y1, y2 to yn be a sample of identically and independently distributed simulation output on performance measure y, and our performance measure has a true mean and true variance, which are often unknown. So in this particular example, y1 represents the number in system at exactly 2 p.m. In replication 1. y2 represents the number in system at exactly 2 p.m. from replication 2. And similarly, yn represents the number in system at exactly 2 p.m. in replication n. So I have this sample of IID simulation output, and I can use this formula to form my confidence interval around my sample mean. So y bar n is my sample mean plus and minus a t-value times square root of my sample variance divided by my sample size, where this tn minus 1 and 1 minus alpha over 2 is the upper 1 minus alpha over 2 critical point of the t distribution with n minus 1 degrees of freedom. So this formula gives me the 100 times 1 minus alpha % confidence interval for my sample mean. In other words, if alpha is 0.05, what I have here is my 95% confidence interval. And what the confidence interval means is that if I create many of these confidence intervals, I expect 95% of them to include the actual value of mu y. So if I generate many of these confidence intervals, I expect 95% of them to actually cover the true population mean of this random variable that I'm trying to estimate. So as you can see, this second component in the expression, which we call the half-width of the confidence interval, determines how wide the confidence interval is really a measure of error, because the wider the confidence interval, the less accurate our estimate of the true population mean. And similarly, the narrower the confidence interval, the more accurate estimate of the population mean. So if I run my model for 100 replications and I see that I have a wide confidence interval, this tells me that I do not have an accurate estimate of my performance measure and that I need to run more replications to reduce my sampling error. So this is why we refer to confidence intervals as measures of error. Now, let's go ahead and talk about risk. In the simulation context, what we generally refer to as risk is essentially the level of uncertainty in the future outcome determined by the distribution of the possible outcomes of our performance measure. So when you think about the sample mean, it is a good single point estimate of the expected long-run performance, but it really doesn't provide any information about the distribution of the possible outcomes of our performance measure. But when you think about the percentiles, they give us some information about the variability and the likelihoods of possible outcomes of our performance measure. So for instance, when I look at the 25th percentile of number and system at 2 p.m., I see that in 25% of my replications, I had less than or equal to 26 or 27 customers in my system. Similarly, when I look at my 75th percentile, I see that my 75th percentile is around 46, 47, which means in 25% of my replications, I had more than 46 or 47 customers in my system at time t. So this is why we refer to percentiles as measures of risk. So to summarize, the confidence intervals in a Moore plot represent measures of error, and percentiles represent measures of risk. Now, suppose instead of the number in system at a particular time t, we're interested in observing and evaluating how the number in system changes throughout the day. In other words, over the 12 hours of operation during a day. So mathematically, for any simulation time t, we let y1 of t be the number in system at that time t from replication 1. y2 of t will be number in system at the given time t from replication 2, and so on. So we have a sample of IID simulation output from n replications for any time t. And as you can imagine, number in system is now a function of time and its distribution also, as well as its population mean and variance, are all a function of time that change with t. In other words, since the distribution of our performance measure is now a function of time, the level of risk and error also change over the simulated time. So in order to analyze how the number in system and measures of risk and error change over time, what we really need is a plot that looks like this. So again, I have my 12 hours, and what I have is a Moore plot for different points in time. And in this case, I'm using 30-minute intervals between my observations. I collect number in system at 30 minutes, 1 hour, 90 minutes, 2 hours, and so on. So here, this particular Moore plot is the Moore plot of number in system at t equals 4 hours, which is 2 p.m. given that our system starts at 10 a.m. So this is the information we need in order to be able to make decisions and evaluate how the number in system changes over time. The problem is there is no easy way of getting this information from any of the existing simulation software packages that we are aware of. Also, ideally, I want to be able to look at how number and system changes over time at different resolutions. So maybe instead of 30-minute intervals between my more plots, I want to use 10-minute intervals between my more plots, or 5-minute intervals. I want to be able to do this without having to run additional simulation replications. And the problem is that getting side-by-side more plots that show change over time requires extensive coding and often leads to excessive replications and redundant replications of the model. I would like to refer you to the conference paper on the AddMore tool if you would like to know more about how you can do this in, for instance, Simio and the downsides of that. So now let's talk about what tools are available to us through commercial simulation software packages that we can use to evaluate how a performance measure changes over time. So remember when we ran our model, we created this dynamic plot that basically shows us how the instantaneous number in system changes as the simulation model is running. So in Simio, if I stop this model and run again, I'm going to get the exact same dynamic plot of my number in system, essentially because Simio is going to use the exact same random numbers to generate my arrivals and my processing times. So in order to be able to see a different scenario using this interactive run, I need to go to Run and Advanced Options, Randomness, and manually change the replication number. So this option essentially changes the initial point in the random number stream that the replication is going to use in order to generate inter-arrival times and processing times. So let's go ahead and change this from 16 to like 2. So now my model is going to use a different set of random numbers to generate my events. So now what I'm going to see is a different plot of number in system. So now you can see in this scenario, the peak is higher during dinner rush than the lunch rush. So I can repeat this process every time I can change my replication number and see how the plot changes. And this will give me some idea about the uncertainty and the variability in the number in system and how it changes over time. But as you can see, it doesn't really give me the statistical information that I need in order to be able to make informed decisions. It doesn't provide the measures of risk and error that I need to be able to make informed decisions. So the other thing that I can do is run multiple of these interactive runs and then simply juxtapose the different dynamic plots and look at the different plots and get a feel for the variability in the number in system over the 12 operating hours. But still, while this gives me a little bit more information because now I can see multiple replications side by side, I still don't have estimates of the measures of risk and error that I need in order to be able to make statistically valid interpretations about number and system over time. The other type of analysis that the existing simulation software packages allow me to do is basically monitor the number and system over time in each replication, write the values to an external file, let's say an Excel file, and then plot a figure like this that presents the resulting sample paths from different replications all in one plot. So here in this plot, I have the sample paths of number and system for 25 replications. And as you can see, there's several issues with this plot. While it provides more information than the previous approach that we talked about, because now we can get an idea about the minimum and maximum number in system at different points in time, and where most of the replications are concentrated. Again, we still can't see useful information about our measures of risk and error and how they change over time. Also, as the number of replications increases, this plot becomes really messy, and extracting any meaningful information becomes extremely difficult. So what I'm going to do next is show you a demo of the Add More Excel add-in that we have developed. So as I said, we have developed a tool, and we call it Add More, Automated Dynamic Display of Measures of Risk and Error, that facilitates analysis of time-dependent statistics that change over time. So here is a sample Add More plot. As you can see, over time, it shows you how measures of risk and error change. So you can make informed decisions about the configuration of your system. So what I'm going to do is, first I'm going to show you quickly how you can generate an Add More plot using the Excel add-in that we've developed. And then I'll talk about how you can collect the data that you need in order to be able to use the tool. And then I'll also talk about a very simple example of how you can actually use the Add More plot in a decision-making context. So let's go to this Excel file that I have here. And in this Excel file, I have all of the data that I need in order to be able to analyze number and system for our little restaurant. So here, as you can see, I have the results for replication 1, 2, 3, 4, and I have the results for 100 different replications of our simulation model here. And what I have recorded in each replication is the value of number in system and the corresponding timestamp or simulation time for that value. So here, this first observation tells me that in replication 1, number in system became 1. In other words, the first customer arrived at this time. And then the number in system goes back to 0 at this time, which tells me that the first customer left the system, while the second customer arrives at this time when my number in system goes to 1. Then the third customer arrives at this time, my number in system goes to 2. And then the second customer leaves the system, my number in system goes back to 1, and so on. I will talk about how you can actually set up your Simio model in order to be able to collect this data shortly. Now, after you download the tool and install it, it's going to appear under the Add-ins tab in Excel. I have the Add More add-in right here, and I can plot my Add More plot. The only thing I want you to know is that you need to have the first data point in your data set selected before you click plot. Otherwise, it's going to assume whatever cell is selected is your first data point in your data set. So again, please pay attention to this little trick here, that before you plot the Add More plot, what you need to do is to select the first data point in your Excel worksheet. Now that I have my first data point selected, I can click on plot, and then you can see the user interface here. So there are a bunch of parameters. I'll talk about these parameters shortly. Most of them have default values that you can use. The only thing that I'm going to set is the offset, which tells me the starting point for my plot. So as you can see, the format is hours and minutes. So I'm going to start my plot from time 0. So I'm going to have 0, 0, 0, 0. Step is the intervals between collecting observations on number and system. So right now I'm going to get hourly more plots for my time in my number in system. The duration is defaulted to all. That means I'm going to plot side by side more plots for all 12 hours of operation. And I also have my percentile values that are defaulted to 25th and 75th percentiles, and the confidence interval, which is defaulted to the 95th percent confidence level. So now if I click draw, what's going to happen is that we're going to get the hourly add more plot for our numbering system. So as you can see, the numbering system at time 0 is of course 0 because the system is empty, and then this is the more plot for hour 1, hour 2, and then time 3. You can see the average numbering system over my 100 replications. You can see its confidence interval, its 75th and 25th percentiles, and their corresponding confidence intervals. You can see the minimum, maximum, and the median of numbering system at exactly t equals 3 hours. So as you can see, I can go ahead and observe how my numbering system changed over time for the system that I'm studying. So let's talk about how we can collect the data that we need in order to be able to generate the add more plot in Simio. So when you think about this, what I really need to do is track the number of customers in my system, and then whenever the numbering system changes, I need to record the new value of numbering system and the corresponding time. In other words, time now in my simulation run. And the way I did it in Simio, there are different ways that you can implement this logic in Simio, but the way I did it was, first of all, I defined a user-defined state variable for my model. So you see I have my model selected here. When I go to definition states, I have this user-defined state variable called NIS, numbering system, and its initial value is 0. And what I do is, in order to track the numbering system, I increment numbering system whenever an entity is created at the source. So when I click on my source object and I go to state assignments, you can see that I have a state assignment logic here. And what I do is I essentially increment my numbering system. So the new value of numbering system is whatever it is plus 1. And then whenever an entity leaves the system, I decrement my NIS value. So again, for my sync object instance, I have a state assignments step. And what I do in this state assignment is I decrement my numbering system. So the new value for numbering system will be NIS minus 1. Now, this will help me track the numbering system during the simulation run. Now, what I need to do is tell Simio to write the value to a file along with the corresponding simulation time whenever this value changes. And the way I implemented this logic in Simio is by defining a monitor element for numbering system. Again, under model definitions elements, I have a monitor element, and the variable that it monitors is numbering system. So that's the state variable that this monitor element monitors. And whenever this value changes, my monitor element triggers a process to run. You see, I have triggered process name, and I call it write NIS to file. Now, let's go to processes and see what this write NIS to file process looks like. And as you can see, it's a simple process with only 2 steps. In the first step, what I do, I increment the row number so that I do not overwrite the numbering system values in my Excel file. And if you look closely, you'll see that every time this process is run, I increment the row number so that I write it in the next row in my Excel file. And this row number, in fact, is a model state variable. So if I go to definitions, states, you see I have the row number state variable. The initial value is 0. So the first time that I'm going to write the numbering system to my file, that's when the first entity arrives. I first increment the row number So it becomes 1, and my right step is going to write the number in system and the corresponding simulation time in row 1 in my Excel file. And then when the next entity arrives, or when the first entity leaves the system, row number becomes 2, and then my right step will write the values in row 2, and so on. Now let's have a closer look at this Excel write step. And as you can see, what it does, it writes to a worksheet called Sheet 1, and the items that are written are as follows. So I have the NIS value, and then time now. So I write two things, the value of number in system and time now. And remember that this process is triggered whenever NIS changes. That's what my monitor step does. I also have this Excel Connect that tells Simio where this Excel file is. So if I go to definitions for my model, under elements, I have an Excel Connect element called Excel Connect 1. And it essentially tells Simio that the Excel workbook or the Excel file is called nis.xls. So now when I go to the directory where this model is, you see I have this Excel file called NIS. And when I open this NIS Excel file, you'll see it's empty. And here is my sheet 1 that I'm going to write the values in. So what I'm going to do now is close my NIS file, go back to my Simio model, and what I'm going to do is I'm going to run the model. And then we're going to go back to our Excel file and see whether the values are written there or not. My run is over, so let's go back to my directory here, open this NIS file. Looks like it's not updated yet. I guess I'll have to go back and stop the model first. So now when I go and open my NIS file, you'll see that the values are written. So in this replication, this is the time that the first customer arrives, first customer leaves, second customer arrives, third customer arrives, and so on. So all of the values of NIS, along with the corresponding simulation times, are written in this Excel file. Now that we know how to collect the data that we need, let's go ahead and talk about a simple example of a decision-making problem. So suppose as the manager of this restaurant, what I'd like to do is first identify the intervals during the day where my number in system, my average number of customers in the system exceeds 20. So I have this goal of keeping the number in system below 20 throughout the day. So what I need is first identify the intervals in which my average number in system exceeds 20, and then I can decide to add additional capacity in order to be able to process customers faster during those intervals and keep the number in system below 20. So what I'm going to do first is do an hourly add more plot. So again, note that I have the first data point in my worksheet selected. So now I can go to the add-ins tab, click on plot on my add more add-in, start at time 0, 1 hour step during the entire 12 hours, 25th, 75th percentiles, and 95% confidence interval for my sample mean. So let's click on draw, and what I see here is the add more plot for 12 operating hours of this restaurant based on 100 replications. So let's just focus on the lunch rush for the sake of this example. And so here is 20. And when I look at my add more plot, I see that while the average number in system at t equals 5 hours is slightly less than 20. Since my confidence interval covers this value, I can't tell for sure that at this point in time, my average number in system is going to be less than 20. Also, you see that at t equals 2 hours, looks like I'm good, but at t equals 3 hours, my average number in system is around 30. But I do not know exactly at which point in time between t equals 2 and t equals 3, my number in system exceeds 20. It can be anywhere in this interval. And also, anywhere between 5 and 6, my number in system, my average number in system, drops below 20, but I don't know what that time exactly is. So if I want to make a decision based on this hourly add more plot, my decision would be add an additional unit of capacity from t equals 2 to t equals 6. So for these 4 hours, I'm going to add additional capacity in order to process customers faster and reduce my number in system. Let's keep that in mind. T between 2 and 6, that's 4 hours of additional capacity, which of course has a cost associated with it. So what I'm going to do is delete this sheet, go back to my data, and this time what I'm going to do is, what I'm going to use is a half an hour step. So now I get a more plot for observations that are collected every 30 minutes. So let's click on draw. I'm going to leave every other parameter to their default value. And now I can go ahead and look at my new add more plot based on 30-minute intervals. So again, I'm going to focus on the lunch rush. And now when I look at this, I see that from 2 to 2:30, it seems that my average number in system will not exceed 20, at least based on my 100 replications. But at some point between 2:30 and 3, it's going to exceed 20. And then on the other hand, when I look at time 5 here, again, I'm not sure if my average number in system is in fact less than 20 here. But it seems that at 5:30, number in system is less than 20, at least based on my 100 replications. But what I do not know is at which point in time exactly between 5 and 5:30, my average number in system drops below 20. However, based on this plot, my decision now would be adding additional capacity from t equals 2.5 hours to t equals 5.5 hours. Now, I know that I'm only going to need 3 hours of additional capacity. So I can go ahead and further improve what I call the resolution of this add more plot. And for example, I can go ahead and plot add more plots for 15-minute intervals, 10-minute intervals, 5-minute intervals, etc. So let me just delete this sheet, go back to my data. First data point is still selected. Plot, I'm going to set this back to 0. And now, instead of 30 minutes, I'm going to do 15-minute intervals. As you can see, it takes a little bit longer to plot it because there's more calculation involved. But here is my plot. So now, again, I can do the exact same analysis and see whether I can save additional money by looking at this data that basically has more accuracy than the previous 2 add more plots that I looked at. It would also be worth noting that while I can increase the accuracy of my add more plot by decreasing the size of the intervals, I should also consider the practical constraints that may exist in the real world. So it may not even be feasible for this restaurant or for this manager to hire additional capacity from t equals 2:30 to t equals 5:30. Maybe due to some regulations, the manager will have to hire additional capacity for at least a certain duration of time, and so on. So again, these practical constraints are other things that you need to keep in mind while making such decisions. The last thing I'm going to do in this video is I'd like to go back and have a look at some other parameters of the add more plot. So suppose what I'd like to do is just focus on the lunch rush, which is from t equals 2 to t equals 6 hours. So what I'm going to do is I'm just going to add a 2-hour offset. So now my first more plot will correspond to t equals 2. Now that I'm limiting my range to a smaller time period, I can use smaller steps. So I can do 5-minute intervals, and the duration of time that I'm interested in is 4 hours. So from 2 to 6, 5-minute intervals. You can change these percentiles. Let's say I'm interested in 20th and 80th percentiles, and maybe a 98% confidence level. So I can click on draw, and now what I'm going to get is an add more plot for t equals 2 to t equals 6 based on 5-minute intervals between my number and system more plots. So now I can do a much more detailed analysis of my number and system during lunch rush. So this concludes our video on the add more plot. As you can see, it's a tool that can become very handy when analyzing time-dependent statistics and observing their behavior over time. So it helps you visualize measures of risk and error over time for such statistics. And again, you can go to my website, ashkannegahban.com, and download the Add More Excel add-in and use it for free.